Right now, most of the universe is invisible to you. Not invisible the way a distant star is invisible. Too far, too faint, too small for the naked eye. Invisible in a different way. Invisible in the way that the thing holding a galaxy together cannot be detected by any telescope ever built. Invisible in the way that something with 5 times more mass than everything you have ever seen, every star, every planet, every cloud of gas, every grain of dust, simply does not appear on any instrument designed to find it. Your room is full of it. The space between you and the ceiling, the space between the Earth and the Moon, the space inside every atom in your body. Something is there, something with gravitational mass, something that bends light and shapes galaxies and determines the large-scale architecture of the entire observable universe. And we have no idea what it is. You feel nothing. Your coffee sits still in its cup. The walls of your room are exactly where they were. Nothing signals the presence of the invisible material threading through everything around you right now. And yet without it, the Milky Way would have flown apart 4 billion years ago. Without it, there would be no galaxies at all. The universe as it exists, with its web of filaments, its clusters, its ordered structure, only works if most of what is out there is something we have never directly seen. Cosmologists call it dark matter. That name is a placeholder, a confession. It is not dark the way a dark room is dark. It does not absorb light. It does not reflect light. It does not interact with light at all. It is dark in the sense that it is simply outside everything we understand. The name says, there is something there, and we do not know what it is. This is not a fringe theory. This is not contested. The existence of dark matter, some form of non-luminous, gravitationally active material constituting approximately 27% of the total energy content of the universe, is one of the most well-supported conclusions in modern physics. Multiple independent lines of evidence from completely different instruments, using completely different techniques, all point to the same result. Something is there. We have measured its gravitational effects to extraordinary precision. We have mapped its distribution across the observable universe. We have watched it redirect the light of entire galaxy clusters. We have built a detailed model of how it has behaved across 13 billion years of cosmic history. We just cannot see it, touch it, or detect it directly. If that interests you, if the idea of an invisible architecture holding the visible universe together is the kind of thing you want to follow to its end, subscribe now. The investigation starts here. The story starts, as many cosmological stories do, with someone looking at something and expecting one result and getting another. The year is 1970. The person is Vera Rubin, an astronomer at the Carnegie Institution in Washington, D.C. The thing she is measuring is rotation curves. A rotation curve is exactly what it sounds like. You pick a galaxy. You measure how fast different parts of it are rotating around the galactic center. You plot the velocity against the distance from the center. That curve is the rotation curve. Now, if you have studied any physics at all, and you do not need much, you know what that curve should look like. We have a very good model for how orbits work. It is the same model that tells us Jupiter orbits the Sun more slowly than Mercury does. It is the same model that tells us the outer planets take longer to complete one trip around the Sun. It is called Keplerian rotation, named after Johannes Kepler, who worked it out in the 17th century, and it works like this. The further from the gravitational center, the slower the orbit. The further out you go, the more the velocity drops off. This is not complicated. This is orbital mechanics as we have understood it for 400 years. If you know where the mass is, you can predict the rotation curve. In a spiral galaxy like the Milky Way, the mass is concentrated in the center, a dense bulge of stars surrounded by a disk that thins as you move outward. This means the rotation curve should look like a hill, fast in the middle, where the stars are dense and the gravitational pull is strong. Then, dropping off toward the edges, where there is less mass, exactly the way the outer planets of the solar system move more slowly than the inner ones. Vera Rubin was measuring rotation curves because she wanted to know if the stars in galaxies actually did what the physics said they should do. She had better instrumentation than anyone before her. She could measure velocities at the edges of galaxies with more precision than had previously been possible. And when she plotted the curves, she did not get a hill. She got a flat line. Not slightly flatter than expected. Not approximately hill-shaped with some deviation at the edges. Flat. The stars at the outer edges of galaxies were orbiting at essentially the same velocity as the stars much closer to the center. In some cases, the velocity even increased slightly with distance before leveling off. The curve had no drop. Whatever physics said should happen, whatever the visible mass of the galaxy predicted, was not what was measured. Rubin understood immediately what this implied. For the rotation curve to be flat, there had to be more mass than you could see. Not slightly more, much more. The mass had to keep increasing with distance from the center, even as the visible matter thinned out and disappeared. There had to be something present, gravitationally active, capable of influencing orbital velocities, that was not emitting any light at all. Something invisible filling the space around and beyond the visible galaxy in a large spherical cloud called a halo. A dark halo. A halo made of matter that could not be seen. She published the results. They were, initially, not believed. Not by everyone. The idea that most of the mass in the universe was invisible ran against everything cosmology had assumed. But Rubin was meticulous. She measured dozens of galaxies, then hundreds. Every single one showed the same flat rotation curve. Every single one required invisible mass to explain it. The result was robust and consistent and reproducible by any telescope capable of the same measurements. This is established. This is confirmed. The rotation curves of galaxies do not match what visible matter alone would produce. Something else is there. Rubin did not name the missing mass dark matter. That term had actually been used earlier, tentatively, by the Swiss astronomer Fritz Zwicky in the 1930s in a completely different context, which we will get to. But Rubin's rotation curve measurements were what made the dark matter problem undeniable. Before her work, it was possible to treat the discrepancy as a measurement error or a theoretical gap. After her work, it was not. The data was too consistent, the sample too large, the discrepancy too large. Something was out there, and it was everywhere. The idea that something might be missing from our mass accounting did not begin with Rubin. It began 40 years earlier with a man who was, by all accounts, one of the most difficult personalities in 20th century astronomy, and also one of its most brilliant. Fritz Zwicky was a Swiss-American astrophysicist working at Caltech in the early 1930s. He was interested in galaxy clusters, the largest gravitationally bound structures in the universe, collections of hundreds or thousands of galaxies held together by their mutual gravitational attraction. The Coma Cluster, a collection of more than 1,000 galaxies, approximately 320 million light-years from Earth, was one of his targets. Zwicky wanted to measure the mass of the Coma cluster. The most straightforward way to do this is to count the galaxies, estimate their masses from their luminosities, and add them up. This gives you the luminous mass, the mass of everything that is shining. Zwicky did this calculation. He also measured the mass a different way. The galaxies inside a cluster are not stationary. They move. They orbit the cluster's center of mass, just as planets orbit the Sun, just as stars orbit the galactic center. If you measure the velocity dispersion, the spread of velocities among the cluster's member galaxies, you can calculate, using a principle called the virial theorem, how much gravitational mass must be present to keep those galaxies bound to the cluster. If the velocities are high, the gravitational pull must be strong, which means the mass must be large. Zwicky measured the velocity dispersion of the Coma cluster. He compared it to his luminous mass estimate. The two numbers were wildly inconsistent. The galaxies in the Coma cluster were moving far too fast to be held by the visible mass alone. If the only gravity came from the luminous matter, the cluster should have flown apart long ago. The galaxies should have dispersed into intergalactic space. But there they were, still clustered, still bound. Zwicky concluded that there must be additional, invisible mass, what he called, in German, Dunkel Materie, dark matter. The phrase was his. His result was largely ignored for decades. This was partly because Zwicky himself was a notoriously abrasive figure who made more enemies than allies. It was partly because the measurement was difficult and the errors were large. And it was partly because the idea was simply too radical. The universe, as most physicists and astronomers understood it, was made of ordinary matter: protons, neutrons, electrons, and the question of where the missing mass came from seemed more likely to have a mundane answer than the exotic one Zwicky was proposing. But Zwicky was right. The Coma cluster is now one of the canonical examples of the dark matter problem. The velocity dispersion of its galaxies requires enormous amounts of invisible mass to explain. Modern measurements, with far better instrumentation, confirm Zwicky's original conclusion. The cluster contains much more mass than its visible galaxies account for. Something unseen is providing the additional gravity. Zwicky's dark matter and Rubin's flat rotation curves are the same phenomenon observed from different angles. One is the motion of galaxies inside clusters. The other is the motion of stars inside galaxies. Both say the same thing. There is more mass than we can see, and the discrepancy is not small. In both cases, the missing mass outweighs the visible mass by a substantial factor. This is not a subtle effect. This is not a small correction. The dark matter, whatever it is not a minor adjustment to an otherwise complete picture. It is the dominant gravitational component of every structure in the universe above the scale of individual stars. The visible matter, the stars, the gas, the dust, the planets, is the exception. It is the minority. The normal matter we are made of, the matter we can see, the matter every instrument we have ever built is designed to detect, constitutes roughly 5% of the total energy content of the universe. 5%. The rest is dark matter and something even stranger, which we will come to. But first, we need to understand how completely convinced cosmologists are that the dark matter is real, because the rotation curves and the cluster velocity dispersions are only the beginning. In 1915, Albert Einstein published his general theory of relativity. Among its many consequences was a prediction that had no precedent in classical physics. Mass bends spacetime, and light, which travels through spacetime, therefore bends around massive objects. This effect is called gravitational lensing. The first confirmation came in 1919 during a solar eclipse, when Arthur Eddington's expedition measured the positions of stars near the sun's edge and found they were shifted by exactly the amount Einstein's equations predicted. The mass of the sun was bending the light from stars behind it. What works for the sun works for anything with mass. A galaxy has far more mass than the sun. A galaxy cluster has vastly more mass than a single galaxy. Gravitational lensing by galaxy clusters should therefore be significant, large enough to distort the images of background objects, to bend light from distant galaxies into arcs and rings and multiple images. And indeed, this is precisely what we see. The Hubble Space Telescope has imaged dozens of galaxy clusters showing dramatic gravitational lensing effects. Distant galaxies whose light has been bent into long, curved arcs by the mass of the foreground cluster. Rings of distorted light called Einstein rings, where a background galaxy is almost perfectly aligned with a massive foreground object. Multiple images of the same galaxy appearing in different positions around the lensing cluster because the light has been bent along different paths. The critical fact about gravitational lensing for the dark matter problem is this. You can use the degree of lensing to measure the total mass of the foreground object. The stronger the lensing, the more mass is bending the light. You measure the distortion, you apply Einstein's equations, you get the mass. And the mass you get from gravitational lensing is consistently, dramatically higher than the mass you get from adding up the visible matter. By how much? Typical galaxy clusters contain 3 to 5 times more dark matter than ordinary matter. Some show even higher ratios. The lensing does not lie. It is light being physically redirected by gravity, and the only thing that produces gravity at these scales is mass. The mass must be there, and since it does not show up in any optical, radio, X-ray, or infrared image, it is dark. What makes gravitational lensing particularly powerful as an argument is that it is an entirely independent method from rotation curves and velocity dispersions. It uses a completely different physical phenomenon, the bending of space-time by mass, measured by a completely different observational technique, using completely different instruments. 3 independent methods: rotation curves, velocity dispersions, gravitational lensing. All 3 produce the same answer: more mass than we can see, much more. But the most striking single observation in the history of dark matter research is not any of these. It is something that happened in 2006, when the results from a collision between 2 galaxy clusters were published, and they changed the argument in a fundamental way. The galaxy clusters in question are collectively called the bullet cluster, though the official designation is 1E0657-558. They are located approximately 3.7 billion light-years from Earth. What is unusual about them is not their distance or their mass. What is unusual is that we are observing them at a moment just after a high-velocity collision. 2 galaxy clusters pass through each other at around 3,000 kilometers per second. That collision happened long enough ago that the aftermath is clearly visible, but recently enough that the components have not fully separated. What we can see spread across the merged region is a complex mixture of visible galaxies, hot gas, and, if the dark matter hypothesis is correct, a large amount of invisible mass. Here is what makes the bullet cluster so important. When 2 galaxy clusters collide, the different components behave differently. The galaxies themselves, vast as they are actually surprisingly diffuse when seen at the scale of a galaxy cluster. The space between individual stars within a galaxy is enormous. So the galaxies inside each cluster during the collision largely pass through each other without interacting. Stars do not collide. The galaxies slow down slightly from gravitational interaction, but they continue outward. The hot gas, the intracluster medium, which makes up the majority of the ordinary matter in a cluster, far more than the stars, does not pass through. Gas has pressure. It interacts electromagnetically. When the hot gas from two clusters collides, it slows down dramatically, piles up, and forms a shock wave. The gas is visible in X-ray observations as a bright region concentrated near the center of the merged system. The distinctive bullet-shaped shock wave gave the system its name. So, after the collision, we have two components of ordinary matter in two different positions: the galaxies, which have moved outward, and the hot gas, which has piled up in the center. We can see both of these directly: the galaxies in optical images, the hot gas in X-ray images. Now, we need to locate the mass. We use gravitational lensing, the same technique as before, to map where the mass is concentrated. And the mass map does not match the X-ray map. The mass is not concentrated in the center, where the gas piled up. The mass is concentrated in two separate clumps, one on each side of the center, corresponding to the positions of the two galaxy clusters after they passed through each other. The mass is where the galaxies went, not where the gas piled up. This is extraordinary. The ordinary matter, the gas, which represents most of the ordinary matter in the cluster, got stuck. It slowed down. It piled up in the center. But the gravitational mass kept going. The mass separated from the ordinary matter. If the dark matter hypothesis is correct, this is exactly what we should see. Dark matter does not interact electromagnetically. It does not interact with the hot gas. It does not slow down in a collision. It passes through, carrying its mass forward with the galaxies. The dark matter from each cluster continued outward, leaving the slowed down gas behind. The lensing maps the mass to where the dark matter went. If there is no dark matter, if the additional gravity comes not from invisible matter, but from some modification of how gravity works, then the mass cannot separate from the gas. The mass of a system is its mass. It cannot separate from itself. Modified gravity theories predict that the mass should stay where most of the ordinary matter is, with the gas in the center. That is not what is observed. The bullet cluster is not the only cluster collision that has been analyzed this way. Dozens of similar systems have been examined since 2006. In essentially every case, the lensing mass is found near the galaxies, separated from the hot gas, consistent with dark matter that does not interact electromagnetically and therefore does not slow down in a collision. This is the observation that most clearly distinguishes dark matter from the main alternative explanations. This is the observation that most cosmologists cite when they say they are convinced dark matter is real. Not a rotation curve, which might theoretically be explained by modifying gravity. Not a velocity dispersion, which involves assumptions about equilibrium. A direct visual separation of mass from ordinary matter during a collision. Documented. Confirmed. Reproduced in multiple systems. The dark matter is real. The question that remains is what it actually is. If you want to understand what dark matter is, you need to understand when it was important, not just now, in the gravity of galaxies, but at the very beginning, in the first few 100,000 years of the universe's existence. When the universe was young, it was hot, extremely hot, dense. The matter and radiation inside it were a single interacting fluid. Photons, protons, electrons, and whatever the dark matter is, all mixed together in a seething, opaque plasma. this was not a quiet state. There were density fluctuations, regions slightly more dense than average and regions slightly less dense. Where there was more ordinary matter, gravity pulled it together, but the pressure of the photon matter fluid pushed back. The result was oscillations, acoustic waves rippling through the plasma like sound waves, but made of matter and radiation rather than air. These acoustic oscillations left an imprint. As the universe expanded and cooled, the photons decoupled from the matter. The plasma became transparent, and those photons streamed freely for the first time, carrying with them the pattern of temperature fluctuations from the acoustic oscillations, frozen at the moment of decoupling. Those photons are still traveling today. We call their distribution across the sky the cosmic microwave background radiation, the CMB. They were emitted approximately 380,000 years after the Big Bang. They have been traveling ever since. We can detect them with microwave telescopes, and they arrive from every direction with almost exactly the same temperature, 2.725 degrees Kelvin. Almost exactly, but not quite. The tiny temperature variations in the CMB, differences of about 1 part in 100,000, encode the entire early history of the universe. They are the baby picture of everything, and they are extraordinarily sensitive to the amount and nature of the matter present at the time they were created. Here is the key distinction that the CMB reveals. Ordinary matter, protons and neutrons and electrons, interacts with photons. It is coupled to the radiation. It participates in the acoustic oscillations. Dark matter, if it exists as the dominant cold, non-interacting component cosmologists hypothesize, does not couple to the radiation. It does not participate in the acoustic oscillations in the same way. It simply provides gravitational pull. It deepens the potential wells into which the ordinary matter oscillates. The shape of the CMB power spectrum, the pattern of how the temperature fluctuations are distributed across different angular scales, is sensitive to both of these components. It tells you not just the total amount of matter, but the ratio of ordinary matter to dark matter and the properties of each. The WMAP satellite, launched in 2001, mapped the CMB with unprecedented precision. The Planck satellite, launched in 2009, mapped it with even greater precision. Both missions produced detailed power spectra, plots showing the amplitude of temperature fluctuations at each angular scale. Those power spectra are not consistent with a universe containing only ordinary matter. The pattern of peaks and troughs in the spectrum, their positions, their heights, their relative amplitudes, requires a component of non-interacting gravitational mass to fit. That component is dark matter. When cosmologists fit models to the Planck data, the best fit has the universe composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, which is a separate mystery we will reach. This is a completely independent measurement from anything involving galaxy rotation or cluster dynamics or gravitational lensing. It uses the physics of sound waves in the early universe, imprinted on photons that have been traveling for 13.8 billion years. And it says the same thing. Dark matter exists. Its abundance is approximately 27% of the total energy budget of the universe. Its ratio to ordinary matter is roughly 5:1. 5 independent lines of evidence: rotation curves, velocity dispersions, gravitational lensing, cluster collisions, and the CMB power spectrum, all pointing to the same component, all quantitatively consistent with each other, all independently derived. This is the most well-confirmed thing we do not understand. Before we ask what dark matter is, it is worth establishing what it is not. Because the first instinct, when told there is more gravitational mass than luminous mass in the universe, is to wonder, could it be ordinary matter that is simply dark? Ordinary matter that is not glowing? Dim stars, failed stars, black holes, neutron stars, cold gas clouds, rogue planets, things made of protons and neutrons, just not shining. Astronomers have a collective name for these objects, MACHOs, for massive astrophysical compact halo objects. In the 1990s, there were serious observational programs to look for them. The technique used was gravitational microlensing. If a massive compact object passed between us and a background star, it would briefly brighten that star through gravitational lensing. A distinctive, symmetric, brightening and fading that is hard to fake with other astrophysical processes. Surveys of the Large Magellanic Cloud and the galactic bulge looked for these microlensing events. If dark halos were made of MACHOs, compact objects between roughly planetary and stellar mass, there should be many such events. There were some, fewer than expected. The surveys concluded that MACHOs could account for perhaps 20% of the dark matter inferred in the Milky Way's halo. Not 100%, not even close to 100%. The galactic dark matter cannot be made of ordinary compact objects of the right mass range to produce the expected microlensing signature. But there is a deeper argument, one that does not depend on surveys or telescopes, one that comes from the physics of the early universe. In the first few minutes after the Big Bang, the universe was hot enough for nuclear reactions. Protons and neutrons combined to form the first atomic nuclei, primarily helium with trace amounts of deuterium, helium-3 and lithium-7. This process is called Big Bang nucleosynthesis, and the abundances of these light elements that it produces are extraordinarily sensitive to the density of ordinary matter, baryonic matter, the technical term for matter made of protons and neutrons. At the time of nucleosynthesis, we can measure the primordial abundances of these elements. We look for very old, very metal-poor stars and gas clouds, systems that have not been significantly altered by later stellar processes, and we measure the helium and deuterium fractions. The numbers we get match the predictions of Big Bang nucleosynthesis at a specific baryon density. That density is consistent with ordinary matter making up roughly 5% of the total energy content of the universe. Not 30%, not 32%, 5%. The ordinary matter, all of it, every proton, every neutron, every atom in every star and planet and gas cloud in the observable universe, adds up to about 5%. The dark matter, at 27%, is 5 times larger. It cannot be made of protons and neutrons, because if it were, the deuterium and helium abundances would not match. Big Bang nucleosynthesis provides a precise measurement of the total baryon budget of the universe, and it is too small to account for dark matter. So, whatever dark matter is, it is not ordinary matter in a non-luminous form. It is not cold gas. It is not rogue black holes, at least not in sufficient quantity. It is not dim stars or failed stars. It is something else. Something whose particles do not interact with photons, do not interact with atomic nuclei in the way protons and neutrons do, but do have mass and therefore gravity. Something new, something outside the standard model of particle physics. The inventory of known particles that physicists have assembled over the past century. Whatever dark matter is, it is not in that inventory. If dark matter is not ordinary matter, then what is it? Physicists have proposed candidates. Some of these proposals are elegant and well motivated by independent theoretical considerations. Some are more speculative. None have yet been confirmed. The most widely studied class of candidates is called WIMPs, weakly interacting massive particles. A WIMP is a particle with mass in roughly the range of 1 to 1,000 times the mass of a proton, the electroweak scale, as particle physicists call it. It interacts with ordinary matter only through gravity and through the weak nuclear force. It does not interact through electromagnetism, which is why it does not absorb or emit light. It does not interact through the strong nuclear force, just gravity and the weak force. The appeal of WIMPs is not arbitrary. In the 1970s and 1980s, theoretical physicists developed a framework called supersymmetry, which proposes that every known particle has a supersymmetric partner. Supersymmetry was developed to solve problems in particle physics that have nothing to do with dark matter. Problems about the stability of the Higgs boson mass, about the mathematical structure of quantum field theory. It was motivated by particle physics alone. But when you do the calculation of what the lightest supersymmetric particle would look like, you find something striking. It would be stable. It would interact only through gravity and the weak force. It would have mass in roughly the electroweak range. And if you calculate how much of it would have been produced in the early universe, you find the answer, roughly the right amount to be the dark matter. This is called the WIMP miracle. The fact that a particle motivated entirely by particle physics happens to have exactly the properties needed to be the dark matter, in exactly the right abundance. This coincidence made WIMPs the leading dark matter candidate for 3 decades. It motivated an enormous experimental effort to detect them, directly, using underground detectors designed to catch the rare recoil of a nucleus when a WIMP bounces off it. Indirectly, by looking for the products of WIMP annihilation in regions of high dark matter density like the galactic center. At particle accelerators, by producing WIMPs in high-energy collisions at the LHC. None of these experiments have found a WIMP. This is not a small thing to acknowledge. The direct detection experiments have become extraordinary. The Lux Zeppelin detector, located nearly a mile underground in the Sanford Underground Research Facility in South Dakota, is a 10-ton tank of liquid xenon, surrounded by layers of shielding and monitoring systems, operating at cryogenic temperatures in an environment so quiet that the researchers can measure individual interactions. It is sensitive to WIMP nucleus collisions at cross-sections orders of magnitude below what was theoretically expected. No signal. No excess events above background. No WIMPs. This does not mean dark matter is not WIMPs. It means WIMPs, if they exist, interact with ordinary matter even more weakly than expected, or they are outside the mass range the current detectors are optimized for, or the theoretical models that predicted the cross-sections were wrong. The parameter space is narrowing. The original, most natural WIMP models are in serious tension with the experimental null results. But WIMPs are not ruled out. The detectors are still running. The search continues. The second major class of candidates is axions. Axions were proposed in 1977 by Roberto Peccei and Helen Quinn, and named by Frank Wilczek, to solve an entirely separate problem in particle physics, the strong C-P problem. Without going too far into the details, the strong nuclear force has a free parameter, a number in the equations, that should, for no known symmetry reason, be able to take any value. But experiments find that it is extremely close to zero. This is called the strong C-P CP problem. Why is this parameter so small? Peake and Quinn proposed a solution involving a new symmetry that, when spontaneously broken, produces a new particle, the axion. Again, this is motivated by particle physics, not by dark matter. The axion was proposed to solve the strong CP problem. But when cosmologists calculated how many axions would be produced in the early universe, they found potentially a lot. Potentially enough to be the dark matter if the axion mass is in a very small range. Much, much lighter than WIMPs, but not zero. Axion searches use different technology than WIMP searches. Axions can, under the right conditions, convert into photons in the presence of a strong magnetic field. Experiments called haloscopes use powerful resonant microwave cavities in strong magnetic fields to look for this conversion. The ADMX experiment at the University of Washington has been searching for axion dark matter for years and has placed constraints on axion masses and couplings across a range of frequencies. No axion has been found, but the accessible mass range is still limited, and the search continues. There are other candidates: sterile neutrinos, hypothetical heavier cousins of the known neutrinos, which might interact even more weakly; primordial black holes formed in the very early universe before any stars existed, which would be dark and gravitationally active. These are constrained, but not entirely excluded, in certain mass ranges. Fuzzy dark matter, an extremely light boson with a mass so small that its quantum mechanical wave properties are significant on galactic scales, which would produce different structural predictions from WIMPs and might explain some anomalies in galactic substructure. Kaluza-Klein particles from theories with extra dimensions. Gravitinos from supergravity theories. The list is long. The field is creative. And the honest summary is this: we have a detailed, precisely measured, observationally robust phenomenon, dark matter, and we have no confirmed particle identity for it. Every motivated theoretical candidate remains undetected. The phenomenon is real. The explanation is unknown. To understand where dark matter is, you have to understand the large-scale structure of the universe. The universe is not uniformly filled with galaxies. Galaxies cluster. They form groups, clusters, and superclusters. And the distribution of these structures across the universe is not random. It is organized. Galaxies preferentially exist along vast filaments, sheets and strands of matter that crisscross the universe like the skeleton of some unimaginably large foam. Between the filaments are enormous voids, regions of space almost entirely empty of galaxies, measuring hundreds of millions of light-years across. This structure, filaments, nodes, and voids, is called the cosmic web. The cosmic web is not visible to the naked eye, and not because it is faint. The individual galaxies in it are perfectly visible, but to see the web, you need to survey hundreds of thousands of galaxies, measure their three-dimensional positions, and plot the whole structure at once. When you do, something extraordinary emerges. The universe, on the largest scales we can map, is threaded with structure. Nodes where filaments intersect, containing the most massive galaxy clusters. Filaments connecting those nodes, and between them, vast emptiness. The cosmic web is made of dark matter, not entirely. The galaxies and gas that trace the filaments are ordinary matter, but the filaments themselves, the scaffolding, the gravitational infrastructure that ordinary matter falls into, are dark matter. This is what cosmological simulations show, and those simulations are one of the most powerful arguments for dark matter that exists. When you take the initial conditions of the early universe, the tiny density fluctuations imprinted on the CMB, and you run a simulation forward in time using only gravity, and you include both ordinary matter and dark matter in the proportions the CMB measurement implies, you get a cosmic web that looks like the one we observe. The same filaments, the same voids, the same cluster masses, the same large-scale topology. When you run the same simulation without dark matter, with only ordinary matter, you get something different. The structures are less pronounced, the filaments are thinner, the clusters are less massive. The whole architecture is less organized. It does not match what we see. The dark matter is the scaffolding. Ordinary matter, being subject to gas pressure and radiation, cannot clump as efficiently on its own. Dark matter, being cold and non-interacting, begins clumping earlier and more efficiently, forming potential wells that the ordinary matter falls into later. Without dark matter providing the gravitational backbone, the large-scale structure of the universe as we observe it could not have formed in the time available. The cosmic web is not just a pattern in galaxy distribution. It is evidence that the dark matter was doing gravitational work in the universe long before any star ever formed. The Millennium Simulation, completed in 2005 by the Virgo Consortium in Germany, used more than 10 billion particles to simulate the evolution of a cubic region of the universe, roughly 2 billion light-years across. The dark matter density field in that simulation, when compared to the observed distribution of galaxies in the same region of the actual sky, matches with stunning accuracy. The same filaments, the same cluster locations, the same statistical properties. That simulation has been superseded by more advanced ones. Illustris TNG, Eagle, the Bolshoi simulation. Each generation more detailed, incorporating more physics, matching observations more closely. And in every one of them, the dark matter is doing the heavy gravitational lifting. It is providing the structure. The galaxies are just the luminous traces of a much larger invisible architecture. When you stand outside on a clear night and look at the Milky Way, you are looking at one galaxy, one bright streak of ordinary matter. What you cannot see is the dark matter halo surrounding it, a roughly spherical cloud extending far beyond the visible disk, containing several times the mass of all the stars and gas combined. You cannot see the dark matter filament connecting the local group, our galaxy cluster, to the Virgo cluster. You cannot see the web, but it is there, measured, confirmed, essential to the existence of everything you can see. The dark matter is not just around galaxies, it is through them. And its distribution inside a galaxy tells you something about its properties that external measurements cannot. When cosmological simulations of dark matter were first compared to the actual structure of galaxies, there was a problem. The simulations predicted that dark matter should pile up steeply in the centers of galaxies, a dense cusp of dark matter at the galactic core. The density should rise sharply toward the center, following a specific mathematical profile called an NFW profile, after Navarro, Frank, and White, the theorists who derived it. But observations of real galaxies, particularly dwarf galaxies, which are small enough that the dark matter dominates even in their centers, suggested something different. The dark matter density profiles in these galaxies looked more like a flat-topped core than a sharp cusp. The predicted steep spike was not there. This became known as the core cusp problem. For years, this was treated as a potential falsification of the cold, dark matter model. If simulations predicted cusps and observations found cores, something was wrong either with the simulations or with the nature of dark matter. The resolution, as best we currently understand it, may lie in baryonic feedback, the complex processes of star formation, supernova explosions, and active galactic nuclei that ordinary matter undergoes. When massive stars explode as supernovas, they drive powerful winds of gas outward from the galactic center. This gas, which was contributing to the gravitational potential well at the center, is suddenly removed. The potential well becomes shallower. The dark matter, responding to the changing gravitational environment, can move outward slightly, redistributing itself into a flatter profile. This is called supernova feedback, and simulations that include realistic models of it produce galaxies with flat dark matter cores rather than cusps. This is a provisional resolution. It works in some simulations better than others. The core cusp problem has not been fully resolved, but the direction of the resolution, baryonic feedback transforming the dark matter distribution, is taken seriously by most cosmologists. There are other small-scale anomalies. The missing satellites problem. Simulations of a galaxy like the Milky Way predict it should have hundreds of small satellite dwarf galaxies. We observe far fewer. Where are the missing satellites? The too big to fail problem. The simulations predict a population of massive dark matter subhalos that should have formed galaxies large enough not to have been suppressed by feedback processes. But those galaxies are not observed. These problems are real, and they are the focus of active research. Proposed solutions include baryonic feedback suppressing star formation in the missing halos, so they exist as dark matter structures without galaxies. Interactions of dark matter particles with each other, self-interacting dark matter, that could smooth out cuspy structures and disrupt massive subhalos. Warm dark matter, particles with higher thermal velocities that erase small-scale structure. The small-scale problems are the most active frontier in dark matter research. They are not evidence that dark matter does not exist. The large-scale evidence, the cosmic web, the CMB, the cluster collisions, is too strong and too consistent for that. But the small-scale problems suggest that either the nature of dark matter is more complex than the simplest models predict, or the physics of how ordinary matter forms galaxies inside dark matter halos is more complex than we currently model. Both of these things are almost certainly true to some degree. In science, when you have a phenomenon that does not fit the existing framework, you have two options. Add new components to the framework, in this case, a new type of particle, or modify the framework itself. For dark matter, the modification route leads to modified Newtonian dynamics, or MOND, and its relativistic extensions. MOND was proposed in 1983 by Israeli physicist Mordechai Milgram. The basic idea is simple. Newton's law of gravity, in its familiar form, breaks down at very low accelerations, specifically at accelerations below a critical threshold called a zero, which has a value of approximately 1.2 times 10 to the minus 10 meters per second squared. 1.2 times 10 to the minus 10 meters per second squared. To understand how small this is, the acceleration due to gravity at the Earth's surface is 9.8 meters per second squared. The critical MOND threshold is roughly 100 billion times weaker than that. At the outer edges of galaxies, where rotation curve discrepancies appear, stars are subject to precisely this very weak gravitational acceleration. Milgram proposed that at these low accelerations, the effective gravitational force is stronger than Newtonian gravity predicts, which would explain why the stars move faster than expected without requiring any extra mass. MOND makes a specific and precise prediction about rotation curves that is not a post hoc fit, but a genuine forecast. Given only the distribution of visible matter in a galaxy, MOND predicts the rotation curve with no free parameters, just the critical acceleration, a zero. And for many galaxies, particularly low surface brightness galaxies, MOND works remarkably well. Not approximately. Well, the predictions match the data in detail that the simplest dark matter models struggle to reproduce. This is not an argument to dismiss. MOND has genuine successes. The baryonic-Tully-Fisher relation, a tight correlation between the total ordinary mass of a galaxy and its asymptotic rotation velocity, is predicted precisely by MOND and is somewhat surprising in the standard dark matter framework. The radial acceleration relation, a correlation between the observed centripetal acceleration of stars in galaxies and the acceleration predicted from the visible matter alone, is a tight, linear relationship that MOND predicts, but that dark matter-only models do not naturally produce. These successes are real and they are taken seriously. MOND is not a crackpot theory. It is a serious scientific proposal with genuine empirical support on galaxy scales. But MOND has problems that are very difficult to solve. The bullet cluster, as described earlier, is a serious challenge. If the mass cannot separate from the baryons, the bullet cluster is unexplained. MOND advocates have proposed answers, mostly involving undetected sterile neutrino dark matter to provide the extra mass, while MOND explains the dynamics. But these solutions are complicated and ad hoc. The CMB power spectrum is a larger problem. The precise pattern of acoustic peaks in the CMB, as measured by Planck, requires a non-baryonic gravitational component to reproduce. The dark matter in the CMB context is not just providing extra mass. It is acting differently from ordinary matter in the acoustic oscillations of the early universe, producing a specific pattern of peak ratios that ordinary matter alone cannot produce. Relativistic extensions of MOND have been proposed that might account for this, but none of them do so as simply or as accurately as the standard dark matter model. The honest assessment is this: MOND is a genuine scientific alternative with real successes on galactic scales and serious difficulties on cosmological scales. Dark matter has real successes on cosmological scales and some difficulties on galactic scales. The comparison is not entirely one-sided, but the weight of the evidence, particularly from the CMB and cluster observations, currently favors dark matter. And no MOND-like theory has yet produced a framework as complete, as predictive, and as broadly successful as the dark matter lambda-C-D-M model. This is a live scientific debate, not fringe, not settled, active. We need to stop here and introduce the second invisible thing, because we have been discussing dark matter, 27% of the universe. But there is something else that accounts for 68%. Something even stranger. Something called dark energy. In 1998, two teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, were using a particular type of exploding star called a Type 1a supernova to measure the expansion history of the universe. Type 1a supernova are useful for this because they have a nearly standard luminosity. If you know how bright they actually are, you can measure how far away they are by how bright they appear. By measuring both the distance and the redshift, the recession velocity, of supernovae at different distances, you can trace how the expansion of the universe has changed over time. The expectation going into this measurement was that gravity should be slowing the expansion. The universe began with the Big Bang, expanded rapidly and should be decelerating as all the matter inside it pulls back on itself. The question was by how much? Enough to eventually stop and reverse, leading to a big crunch? Or just decelerating but continuing forever? Neither team found deceleration. They found acceleration. Distant supernovae were fainter than expected, meaning they were farther away than they should be if the expansion were decelerating. The universe was not slowing down. It was speeding up. The expansion of the universe is accelerating. This result was so unexpected, so inconsistent with every prior understanding, that both teams spent years checking their work before publishing. When they did publish, in 1998, it changed cosmology permanently. The 2011 Nobel Prize in Physics was awarded for this discovery. The acceleration requires an explanation. Gravity, the only long-range force that acts on matter at cosmological scales, is attractive. Gravity decelerates expansion. For the expansion to accelerate, there must be something doing the opposite. Something with negative pressure. Something that acts like a repulsive contribution to the energy content of space. This is dark energy. Dark energy does not cluster. It does not form halos or filaments. It is smoothly distributed, apparently uniformly, throughout all of space. It does not interact with matter in any way we can detect, except through its effect on the overall expansion of the universe. It is, in Einstein's general relativity, a perfectly legal possibility, what Einstein called the cosmological constant, a term in his field equations representing the energy density of empty space itself. Einstein introduced it, then called it his greatest blunder. Then it came back. The simplest model of dark energy is a cosmological constant, a fixed energy density of the vacuum. This model fits all existing observations extremely well, but it comes with a theoretical problem of such staggering proportions that it has been called the worst prediction in the history of physics. When particle physicists calculate the quantum mechanical contribution to the vacuum energy, the energy of empty space arising from quantum field fluctuations, they get a number. The number they get is approximately 10 to the power of 120 times larger than the dark energy density we observe. A factor of 1 followed by 120 zeros. This discrepancy is not a small theoretical problem. It is the largest fine-tuning problem in physics. Why is the vacuum energy so extraordinarily smaller than quantum mechanics predicts? We do not know. There is no satisfying answer. The cosmological constant fits the data. Its theoretical value is incomprehensible. Both of these things are true simultaneously. Alternative models of dark energy, called quintessence, involving a dynamical field that can vary in time, are observationally viable, but have not been confirmed to be anything other than a cosmological constant. The Euclid satellite, launched in 2023, and the Dark Energy Spectroscopic Instrument, or DESE, both at various stages of operation, are designed to measure whether dark energy has been constant over time or has evolved. Early results from DES, I suggest it may be possible that dark energy is not a fixed constant, but something that changes. Though these results are preliminary and require more data. Dark energy is the dominant component of the universe. 68%. It is driving the long-term fate of everything. As it continues to accelerate the expansion, galaxies will recede from each other faster than light. In roughly 100 billion years, galaxies beyond the local group will cross the cosmic horizon. Not gone, but unreachable, invisible, effectively removed from the observable universe. In a trillion years, future civilizations within the local group will look out at a universe that appears almost empty. The cosmic web will be unreachable. The evidence for the Big Bang will have redshifted to undetectable wavelengths. They will think the universe is just the local group, unless they have records from the present, records of a time when the whole web was still visible. We are alive in the window when the universe is still legible. Let us return to dark matter and to the people spending their careers trying to find it. The Lux Zeppelin experiment, or LZ, is located in the Homestake Mine in Lead, South Dakota. The mine is 1.5 kilometers underground. The rock above is shielding. The target is cosmic ray muons, high-energy particles from space that could fake a dark matter signal. At 1.5 kilometers of rock, the muon flux is reduced by a factor of 10 million compared to the surface. Inside the mine, LZ consists of an outer detector, a liquid xenon skin layer, and the inner detector, 10 tons of liquid xenon cooled to minus 101 degrees Celsius. When a dark matter particle strikes a xenon nucleus, the recoil would produce a tiny flash of light and a small electrical signal. The ratio of these two signals identifies the nature of the interaction. A genuine WIMP signal looks different from a background gamma ray or neutron interaction. The detector is surrounded by a 228-ton tank of liquid scintillator to veto neutrons and gammas, then by ultra-pure water to absorb radiation from the surrounding rock. Every component was manufactured from materials chosen for their extremely low radioactivity. The detector is so sensitive that trace amounts of radioactive uranium and thorium in ordinary concrete would overwhelm it. The rock walls of the mine had to be carefully characterized. The researchers themselves are a source of background radiation. First results from LZ were published in 2023. They set the world's most stringent limits on WIMP nucleon spin-independent interactions across a range of WIMP masses from 9 to 1,000 times the proton mass. No signal. The analysis found no statistically significant excess above background. The sensitivity reached 9.2 times 10 to the minus 48 square centimeters for a WIMP mass of 30 times the proton mass. To contextualize that number, 9.2 times 10 to the minus 48 square centimeters is a cross-section so small that if you filled the entire volume of the Earth with liquid xenon and ran your experiment for the age of the universe, you might detect one event. The detector is that sensitive. The signal is not there. This is frustrating, but it is also informative. Every null result is a constraint. Every constraint narrows the parameter space. The regions of WIMP mass and interaction strength that are consistent with the dark matter abundance and with the experimental limits are getting smaller every year. Either the WIMP is at the very low end of the accessible mass range, or at very low interaction cross-sections, or it is not a WIMP at all. Simultaneously, the axion searches have been growing in scope and ambition. The Haystack experiment at Yale, the ADMX-EFR experiment, and the Abracadabra experiment at MIT are all searching for the conversion of axion dark matter into photons. These experiments probe different mass ranges and use different detection techniques. The landscape of axion searches is expanding rapidly, motivated by the growing tension between WIMP null results and the increasing theoretical interest in axion models. There is also a remarkable new program searching for ultralight dark matter candidates using atomic interferometry and precision quantum sensors. The idea is that extremely light dark matter particles, with masses far below anything LZ could detect, would produce tiny oscillating forces on ordinary matter, detectable only with quantum-limited sensors. programs using atomic clocks, gravitational wave detectors like LIGO, and purpose-built quantum sensors are looking in mass ranges that were previously inaccessible. None have found anything yet. But the experimental frontier is alive and expanding. The dark matter has not been found. The search has not stalled. The tools are getting better. If dark matter particles can annihilate with each other, if a dark matter particle and its antiparticle can meet and convert into ordinary matter, then regions with high dark matter density should produce a detectable flux of annihilation products: high-energy gamma rays, positrons, antiprotons, neutrinos. The center of the Milky Way is the obvious target. Dark matter density is expected to be highest there, in the gravitational center of the galaxy's dark matter halo. The Fermi Gamma Ray Space Telescope, launched in 2008, has been mapping the sky in gamma rays with unprecedented sensitivity. And there is something interesting at the galactic center. Since around 2012, a number of analyses have found an excess of gamma rays from the galactic center above what standard astrophysical models predict. The excess has a spectrum, an energy distribution, that is consistent with what you would expect from WIMP annihilation at a mass of roughly 30 to 50 times the proton mass. The spatial distribution is roughly consistent with the expected dark matter density profile. The excess is statistically significant. Multiple independent teams have confirmed it is there. But confirming that an excess is there is not the same as confirming it is dark matter. The galactic center is one of the most complex regions of the sky. It contains a supermassive black hole, intense star formation, many types of pulsars and other neutron stars, shock-heated gas, cosmic ray sources. Any of these could be producing gamma rays that contribute to an apparent excess. The most competitive ordinary astrophysics explanation for the galactic center excess is an unresolved population of millisecond pulsars, rapidly spinning neutron stars that have been spun up by accretion from a binary companion and now emit gamma rays. There are known millisecond pulsars in the galaxy, and their gamma ray spectra are similar to what the excess shows. If there are enough of them, concentrated toward the galactic center, they could produce the observed signal without any dark matter. Distinguishing these possibilities is hard. The excess has a smooth appearance, which you might expect from dark matter, but not from a population of discrete point sources. But if the point sources are too numerous and too faint to individually resolve, they could mimic a smooth distribution. Improved analyses using more sophisticated statistical techniques have tried to determine whether the excess is intrinsically smooth or composed of many unresolved points. The results are inconclusive. Different analysis teams reach different conclusions. As of now, the galactic center gamma ray excess is real, unexplained, and consistent with dark matter annihilation, but not confirmed to be dark matter. It remains one of the most intriguing unresolved signals in astrophysics. There have been other tentative signals over the years. A 3.5 kilo-electron-volts X-ray line, a narrow spectral feature at 3.5 kilo-electron-volts, was detected in 2014 in the spectra of galaxy clusters and the Andromeda Galaxy. It was proposed as a signal of sterile neutrino dark matter decaying. The line has been confirmed by some instruments and not seen by others. The situation is unresolved. The Athena X-ray Observatory, scheduled for launch in the 2030s, may finally have sufficient sensitivity to determine whether the line is real and whether it is astrophysical or exotic in origin. The pattern of indirect detection is the same as direct detection. Intriguing signals that require follow-up, null results in well-constrained mass ranges, and an ever-refining landscape of possibilities. The Large Hadron Collider at CERN, near Geneva, is the most powerful particle accelerator ever built. It accelerates protons to 99.9999991% of the speed of light and collides them at a center of mass energy of up to 14 tera-electron volts. The detectors, ATLAS and CMS, monitor the products of these collisions with billions of sensor elements, recording millions of collision events every second. The LHC discovered the Higgs boson in 2012. This was the final predicted particle of the Standard Model of Particle Physics, and its discovery was a triumph of both theoretical and experimental physics. The Standard Model is now complete, in the sense that all its predicted particles have been found. But the LHC was also supposed to find new physics, supersymmetric particles, dark matter candidates, signs of extra dimensions, particles from other theoretical frameworks beyond the Standard Model. It has not found them. This is the most important null result in particle physics of the past generation. The absence of new physics at the LHC, after 2 complete runs at the highest collision energies ever achieved with the most sensitive detectors ever built, is a significant fact. It does not mean new physics does not exist. It means new physics, if it exists, is not at the energy scale the LHC accesses. WIMPs, if they are produced at the LHC, must be produced in numbers too small to be detected, or with properties that make them invisible to the current detectors. The LHC will run through the end of the 2030s, with planned high-luminosity upgrades that will collect far more data. The more data collected, the deeper the sensitivity to rare processes. There is still physics to be found, and there are proposals for more powerful accelerators. The Future Circular Collider, or FCC, proposed at CERN, would be a 100-kilometer ring accelerating protons to 100 tera-electron volts, roughly 7 times the energy of the current LHC. At those energies, new physics that is currently beyond reach might become accessible. The FCC is not approved or funded, but the physics case is being actively developed. The honest summary of collider searches for dark matter is: no signal at existing energies, clear motivation to explore higher energies, and a timescale measured in decades. There is an aspect of dark matter's role in the universe that is less often discussed than its effect on mature galaxies, but that may prove important for understanding its nature. Its role in the formation of the very first structures. After the CMB photons decoupled from matter at 380,000 years, the universe entered a period called the Cosmic Dark Ages. There were no stars. There was no starlight. The universe was filled with neutral hydrogen gas and dark matter, slowly cooling, with dark matter density fluctuations growing under gravity. This lasted for perhaps 100 to 200 million years. The first structures to form were dark matter halos, knots of dark matter where density fluctuations had grown enough to stop expanding with the universe and begin collapsing. Ordinary matter fell into these halos. The gas cooled and condensed. Eventually, in the densest, most massive halos, the gas fragmented and collapsed into the first stars. These first stars, called population 3 stars, were very different from stars today. The gas from which they formed contained only hydrogen and helium, with no heavier elements. Without the cooling provided by heavier elements, the gas fragments were larger, and the first stars are believed to have been far more massive than typical stars today, perhaps hundreds of times the mass of the Sun. This is not confirmed. we have not directly detected population 3 stars. They would have been extremely bright, but extremely distant, and they would have lived very short lives before exploding as supernovas and seeding the universe with the first heavy elements. The James Webb Space Telescope, launched in December 2021, is capable of observing galaxies from the first few 100 million years of the universe. There have been detections of galaxies at redshifts approaching 15, less than 300 million years after the Big Bang. Indirect evidence for population 3 stars in these early galaxies is being actively sought. The point for the dark matter story is this. The nature of dark matter determines the mass scale of the first halos that form, which determines the mass of the first stars, which determines the first supernova explosions, which determines the first seeding of heavy elements, which ultimately contributes to the timeline of when planets and chemistry and life become possible. The identity of dark matter is not an abstract particle physics question. It is connected to the entire history of how the universe became habitable. Warm dark matter, with its higher thermal velocities, would have suppressed the formation of small dark matter halos in the early universe, delaying the formation of the first structures compared to cold dark matter. Self-interacting dark matter would affect the density profiles of the first halos. Axion dark matter, depending on its mass, might produce different patterns of early structure formation. The next generation of telescopes, including JWST, the Roman Space Telescope, and the extremely large telescope on the ground, will probe the early universe with enough detail to constrain the nature of dark matter through its effects on early structure formation. The search for dark matter is not in retreat. It is expanding, diversifying, and becoming more precise. The null results of the past decade have not ended the field. They have redirected it. The original, most natural WIMP candidates in the most natural mass range have been ruled out or severely constrained. This is progress. This is the scientific method working exactly as it should. A hypothesis is tested, the hypothesis is constrained, the parameter space is explored, new hypotheses emerge, better experiments are designed, the direct detection experiments will continue to improve. LZ will accumulate more data and increase sensitivity. The next generation of xenon experiments, XLZ-D, a proposed ton-scale successor, would push sensitivity by another order of magnitude, essentially exhausting the theoretically motivated WIMP parameter space. If no signal is found at that scale, the WIMP hypothesis will be very difficult to maintain in its standard forms. If a signal is found, it will be one of the most important discoveries in the history of science. The axion searches are entering a golden era. New experimental techniques using superconducting quantum circuits, nuclear magnetic resonance, and astronomical observations of strong magnetic fields are opening mass ranges that were previously inaccessible. The Casper experiment and its variants, the Alpha experiment, and a range of astrophysical tests are collectively mapping the axion parameter space far more rapidly than was possible 5 years ago. The Euclid satellite and DESI are producing the largest three-dimensional maps of the universe ever made. These maps trace the large-scale structure, the cosmic web, with a fidelity that will constrain the properties of dark matter through its effects on structure formation at multiple scales. They will also constrain dark energy, both mysteries in a single dataset. The Vera Rubin Observatory, named after the woman who measured the first flat rotation curves, is set to begin full survey operations in the late 2020s. Its Legacy Survey of Space and Time, LSST, will image the entire southern sky every few nights for a decade, cataloguing billions of galaxies and millions of transient events. Among its dark matter deliverables, the most precise measurements of weak gravitational lensing ever achieved, essentially mapping the dark matter distribution across a significant fraction of the observable universe. It will also search for primordial black holes through microlensing at a scale that dwarfs previous surveys. Gravitational wave detectors may contribute. If dark matter consists of compact objects, primordial black holes, for instance, in certain mass ranges, LIGO, Virgo, and their successors may detect their merger signatures at rates that would discriminate between dark matter and astrophysical population models. The Square Kilometre Array, or SKA, a network of radio telescopes in South Africa and Australia with a total collecting area of 1 square kilometre, will map neutral hydrogen emission across an enormous volume of the universe. Among its capabilities, rotation curve measurements for millions of galaxies, constraining dark matter properties through the detailed dynamics of the full galaxy population rather than one galaxy at a time. The Athena X-ray Observatory will examine the 3.5 kilo-electron-volt line question and will also probe the intra-cluster medium of galaxy clusters in new detail, examining the interplay of dark matter and ordinary matter in the most massive structures in the universe. This is what the next 15 years looks like. Not one experiment, not one technique, but a diversified, multi-wavelength, multi-scale, multi-method assault on the invisible architecture of the universe. We have spent this entire investigation in the domain of the well-confirmed, the flat rotation curves, the velocity dispersions, the lensing maps, the bullet cluster, the CMB power spectrum. These are not contested. These are the data. Whatever dark matter is, these phenomena are real, and they demand an explanation. But there is a deeper question underneath all of this, one that physics is just beginning to formulate with any precision. It is not. What particle is dark matter? That is a question we are actively trying to answer. The deeper question is, why does the dark matter have approximately the right amount of mass to produce the structures we see? Why is the ratio of dark matter to ordinary matter roughly 5:1? Why is the dark energy density small enough that the universe could form structure at all? Why do these seemingly independent components, the baryons, the dark matter, the dark energy, have the values they do and not wildly different ones? This is called the cosmic coincidence problem, or in some formulations, the fine-tuning problem of cosmology. And it has no satisfying answer. One direction physicists look is the multiverse. If there are many universes with different values of these parameters, and if we necessarily find ourselves in one where the parameters allow the existence of observers, then the values we measure are not surprising. They are selected. This is called the anthropic principle. It is not universally accepted. Many physicists regard it as untestable and therefore unscientific, but it is taken seriously as a logical possibility. Another direction is the idea that the parameters are related by some deeper physical principle we have not yet discovered. That the ratio of dark matter to baryons is not a coincidence, but a consequence of some symmetry or mechanism in the early universe that we have not yet identified. This would imply new physics, potentially at scales accessible to future experiments. The honest answer is, we do not know. The universe has a composition 5%, 27%, 68% that we can measure precisely and cannot explain theoretically. The precision of the measurement and the absence of theoretical explanation sit side by side, both clearly established, neither yet resolved. Sit with this for a moment. Everything you have ever seen, every star you have looked at, every galaxy in every photograph, every nebula, every planet, every moon, every asteroid, every grain of dust between the stars, constitutes 5% of the universe. Not 5% of some local region, 5% of everything. The rest is invisible. Not dark in the sense that it is night and we could turn on a light. Dark in the sense that it does not interact with light at all. Dark in the sense that no electromagnetic instrument, no optical telescope, no radio dish, no X-ray satellite, no gamma-ray detector can see it directly, and yet it is the reason you exist. Without dark matter, the density fluctuations in the early universe would not have grown fast enough to form galaxies before the expansion pulled everything apart. Without galaxies, there are no stars. Without stars, there is no carbon, no oxygen, no iron, no heavy elements at all. Without heavy elements, there is no chemistry. Without chemistry, there is no biology. Without biology, there is no one to notice that the universe is mostly invisible. The dark matter is not a curiosity. It is the scaffold on which your existence hangs, and we do not know what it is. That is not a failure. That is the frontier. That is where knowledge ends and investigation begins. The measurements are precise. The phenomenon is real. The particle, or particles, or field, or whatever it actually is, remains unconfirmed. The detectors are underground and running. The satellites are in orbit. The colliders are accelerating. The theorists are proposing. The universe is waiting. The Vera Rubin Observatory will image 1 billion galaxies. LZ will push direct detection sensitivity to the edge of the theoretically motivated parameter space. Euclid is mapping the cosmic web. JWST is peering into the first few 100 million years of the universe, watching the dark matter halos light up as the first stars form. Every one of these instruments is a different angle on the same question. Something is filling the universe. It has 5 times more mass than everything we can see. It shaped every structure that exists. It is here, in the space around you, between the atoms in the air, moving through the Earth itself at millions of particles per second, undetected, unnamed, present. The investigation is ongoing. The question is open. And we are the species in the one brief window of cosmic history when the universe is still legible, doing the work of finding out. In 1933, Fritz Zwicky looked at a cluster of galaxies and found that the galaxies were moving too fast. He thought something was missing. In 1970, Vera Rubin measured the rotation curves of galaxies and found that the edges were not slowing down. She thought the same thing. Something was missing. Not a little missing, enormously, overwhelmingly missing. The visible matter was a small fraction of what had to be there. 50 years later, we have mapped that missing thing across the entire observable universe. We have watched it separate from ordinary matter in a collision. We have seen its imprint in photons that have been traveling since 380,000 years after the Big Bang. We have simulated a universe with it and got the cosmic web we observe, and simulated a universe without it and got something that does not look like home. We know more about something invisible than most people know about what is visible, and we still do not know what it is. That is the state of things. Not a failure, not a mystery that refuses to yield. A mystery at exactly the right stage, defined precisely enough to investigate, open enough to surprise us, deep enough to matter. The instruments are running. The parameter space is narrowing. Somewhere in the data already collected, or in the data being collected right now, or in the data that will be collected in the next 15 years, there may be the answer. A small excess above background in a ton of liquid xenon a mile underground. A spectral line in the X-ray spectrum of a galaxy cluster. An anomaly in the weak lensing map of a billion galaxies. A pattern in the cosmic web that distinguishes cold, dark matter from warm dark matter, from axions from primordial black holes. Or we will find something no one has thought of yet. Something that makes all the current candidates look like wrong guesses in the right direction. That happens. It happens more often in physics than the textbooks suggest. Right now, whatever dark matter is, it is passing through you at a rate that depends on its mass and cross-section. Numbers we do not know. It is passing through the Earth. It is passing through every galaxy in the observable universe. It has been there since before the first stars. It will be there after the last ones. It has no beginning and no end that we can trace. Only a presence we can infer from the way visible things move. You are inside it. You have always been inside it. It is just that we are only now, in this particular window of cosmic history, starting to find out what it is.